Professor, so we will be taking the questions at the end. Will that be fine?
Oh yeah, that's fine.
So
that is not a problem at all.
Yeah. So they can type or write the questions, and then we can to go with the flow. After that thing, we can at the end.
Yeah, not a problem. As long as you remember the slide number and so on and so forth, it's just perfectly okay.
Yes. Hello, working, sir?
Everything's fine.
No, actually our BG sir joined. Hello, sir, can you hear us? Working, sir, can you hear us?
Yes, I can hear you.
Yes, sir. So we will be waiting for 1 minute, and then we can start.
Yes, sure.
Yeah, sure. Thank you, sir. Good morning, good afternoon, and good evening from wherever you are joining in this seminar. So I'm very happy to share that today we have among us and very pioneer engineer and a physicist, Professor B. Shankaran with us, who would be sharing his discussions with us, sharing his valuable insights on his work. So we had with us Professor Brotin Ghosh from Department of Electronic and Electrical Communication. So I would request Professor Ghosh to kindly introduce Professor Shanker.
Welcome everybody to this session of the lecture by Professor B. Shanker. We are indeed very happy that he had accepted our invitation and agreed to deliver this lecture and this talk. So I will just begin with a brief introduction of Professor Shanker. Professor B. Shanker received his B.Tech from the Indian Institute of Technology, Madras in 1989. MS and PhD in 1992 and 1993 respectively from the Pennsylvania State University. From 1993 to 96, he was a research associate in the Department of Biochemistry and Biophysics at Iowa State University, where he worked on the molecular theory of optical activity. From 96 to 99, He was with the Center for Computational Electromagnetics at the University of Illinois at Urbana-Champaign as a visiting assistant professor, and from 1999 to 2002 with the Department of Electrical and Computer Engineering at Iowa State University as an assistant professor. Currently, he is a university distinguished professor, an honor accorded to about 2% of MSU faculty members in the Department of Electrical and Computer Engineering at the Michigan State University and the Department of Physics and Astronomy. From 2015 to 2018, he was appointed Associate Chair of the Department of Computational Mathematics, Science and Engineering, a new department at MSU, and was a key player in building this department. Earlier, he served as an Associate Chair for Graduate Studies in the Department of Electrical and Computer Engineering from 2012 to 15, and currently is the Associate Chair for Research in ECE. He has co-authored around 450 journal and conference papers and presented a number of invited talks. His research interests include all aspects of computational electromagnetics, frequency and time domain integral equation based methods, multi-scale fast multipole methods, fast transient methods, higher order finite element and integral equation methods, propagation in complex media, mesoscale electromagnetics, and particle and molecular dynamics as applied to multiphysics and multiscale problems. He was an associate editor for IEEE Antennas and Wireless Propagation Letters and IEEE Transactions and Antennas and Propagations. He is the topical editor for Journal of Optical Society of America A and is a full member of USNC ERSI Commission B. He is a fellow of IEEE, elected for his contributions in computational electromagnetics. He has also been awarded the Withrow Distinguished Junior Scholar in 2003, the Withrow Distinguished Senior Scholar in 2010, the Withrow Teaching Award in 2007, and the BL Outstanding Faculty Award 2014. With that, I would hand over to Professor Shanker.
Thank you, Bratin. It's wonderful to, well, I can't see you right now because I'm looking at my screen on my iPad, but it's wonderful to hear from you again, and thank you for reaching out to me. Hope all of you are doing much better. And it's very scary to hear about what's going on in India from 8,000 miles away. So that said, like I was saying earlier, I think the plan is for you guys to ask me questions. I typically, if I were presenting live, I would ask you to stop me at any point so that we can discuss nuances. But feel free to ask whatever questions you feel like at the very end. So with no further ado, what I'm going to try and discuss today is essentially is computational methods that we have developed over the years for high fidelity electromagnetic simulations. And my hope is that by the end of this particular talk, a lot of you will be very animated and excited about a lot of new problems that are coming down the pipe. So hopefully all of you can see the screen. If not, please yell. Okay. So this is approximately the outline I'm going to follow. I'm going to give you a brief background and introduction. And then I'm going to introduce to you the notion of geometry, and I'm going to take you back a few steps in terms of what geometry is, and from that perspective, I mean, a lot of this will relate to what you guys currently do on your iPhones and tablets and all of that kind of stuff. Then I'll talk about how we define physics on the geometry and what you can do with physics on the geometry. And then I'll slowly drift over into what are the new different integral equations that you can formulate, or all of that kind of stuff, and how you can parallelize it, and how you can actually, at the end of the day, solve problems that are very, very, very real. And that is always a challenge. Okay, and then I'll conclude my talk and outline directions that our group is following. So to give you a bit of a background, in terms of computational electromagnetics, we'd like to define it as a scientific discipline, if you want to think about it, a subset of electromagnetics in general, wherein we're really trying to figure out how does one solve Maxwell's equations to a very high degree of accuracy. So that's one buzzword. as well as efficiently. That's the next best buzzword. So in other words, you want to solve it very accurately and highly efficiently. And those two things, as you probably well know, they don't quite go together. So we are essentially laying out a path as to how this is possible. So as you can imagine, if you stand back, Maxwell's equations in some sense govern all of electromagnetic theory, and its applications are beyond realms. I mean, if you think these days about automation, you think about self-driving cars and all of that kind of stuff, all of that relies on Maxwell's equations in one way or the other. If you sit in a modern car, the environment that you're surrounded by is electromagnetically dense, right? I mean, you can think of all the radios, everything radiating around it, that should, in some sense, function without interference. So that is an enormous challenge, right? And you can imagine a number of different applications. I don't need to tell this community about it, but there are a huge bunch of applications. So, okay, so a huge bunch of applications. So let's look at a prototype problem. I thought I was missing a slide. But this is typically what we do, right? I mean, we are given a domain that we want to try and figure out what the fields are. What does that mean? That you're given a boundary, you're given a volume, you're given some kind of an excitation. It can either be an antenna or you are irradiating something. And your goal in any of these scenarios is to really find the entire field description or a means to find this field description, either near or far, localized quantities like impedances, and you're going to solve this problem either in time and or frequency domain. So let's look at a couple of problems. So this is a toy aircraft, and essentially what I'm doing here is I'm illuminating it with a wave. Now, this is something that you're going to see again and again, is that we need to give it a measure of size. So the measure of size of this particular aircraft, we're going to normalize it with respect to wavelength. So this aircraft is 64 wavelengths long. And if you think about it, that's a very, very large object. So a small dipole is, half a wavelength long, and that's it. A sphere, a small dipole is a half a wavelength long. That's the pattern that it produces. So you can imagine that as the size increases, the patterns become richer and richer and richer. So our goal in this first figure is to really look at what are the currents that are induced on this particular aircraft, because at some point we'd like to figure out what is the signature of this particular aircraft as observed by a radar system. So that is really, so finding the current is an intermediate step to finding its signature. That's one particular application. Another particular application is, say, you are in a tower somewhere, you're essentially trying to figure out what are the communication pathways in a dense urban environment. And you can imagine that it is dense, it is very, very heterogeneous in the sense that it has glass, it has concrete, it has rebar, it has people moving around, it has cars buzzing around. And your goal is to try and figure out what is a good location of all of these towers so you have optimal coverage. So another example, so these are two different examples for in some sense. So if you go back and looking at the time that I spent on this, and some of you might say that this is longer than ages, but if you look at the time that people have been working on it, there was a huge revolution sometime in the early 90s, right? And people really figured out how to develop some of these methods. So if you go back in time, and I think there's a very illustrative example, if you go and look at irradiation cell phone development. So you can imagine a long time ago, cell phones were about the size of a regular brick, right? And they were huge with an antenna on top. And what people are interested in when they first started out, and it's still being done to this day, is how much power is deposited in a person's tissue if they're holding it right next to them. And at that point, everybody's head was modeled as a sphere, right? Essentially, people looked at a wire with a certain amount of input power and how much of that energy would penetrate a phantom, and all our heads were essentially modeled as one wonderful sphere of a certain size. Obviously, not all of us are spherical. So as you went forward, I mean, modeling spheres was reasonably an easy task. But as one wanted to add more features, say a nose and eyebrows and hair, and more recently, properties of tissue, properties of blood vessels, and how is blood transported from a point to another point. I mean, as you go, in other words, as you add more fidelity and as you add more detail, you can imagine that the cost of this simulation is going to go through the roof. And that essentially was the driver. The driver was, how do you capture fidelity? Geometric fidelity, structural fidelity, material fidelity within any simulation tool, because that is an integral part of a design process. And if you look at how far we have come from about mid-1990s to about now, we have grown leaps and bounds. So if you think about a regular workflow, if you go out into a company, and when I talk to my students who are working at Intel, or if you've gone to any IMS meeting, one of the questions that is asked now more often than not is not whether the experiments, whether you're compared against experiments, which was kind of the de facto question earlier. It is, have you compared it against HFSS? I mean, so the tools of the trade have become incredibly trustworthy. And in some sense, it is thanks to a number of different players, academics who essentially figured out what are the right. Go ahead. Sorry, was that a question?
No, it was a disturbance, I guess. So participants, once again, I would ask all of you to kindly mute yourself so that we could have the flow. Thank you.
So in some sense, what has happened is academics developed the right mathematical tools, showed that this would work, essentially pushed the boundaries in terms of making a lot of these methods accessible to the wider community, as well as building tools that are efficient. And people in companies like Ansoft and FICO essentially took it upon themselves to take these tools and essentially run with it. Right. So much so that when I talk about HFSS, it really is an Ansoft tool, and that's a moniker for all computational tools. Okay, this is what I'm comparing against. Does your code do the experiments match against this? If not, why not? If yes, well, why yes? I mean, what are the approximations that you made? Do these make sense? So in some sense, there is a tendency now to think that all is done, but far from it. As I'll show you in a minute, right? There are very, very interesting challenges as you go down. Right? One example that I talked to you about was the feature sizes. So the feature sizes continue to shrink. People are more interested in details. People are more interested in impedances at a given point. There is incredible amount of material complexity. So if you just dial back and think of additive manufacturing for now, and additive manufacturing is going through the roof, right? I mean, so if you think of things that you can just print out, there is enormous surface inhomogeneity, for instance. There's enormous material inhomogeneity. And all of these affect the local electromagnetic structure, and therefore the model. So you can actually, you can come on and say, I want to design this very weird structure, and you can potentially print it, provided you know all the details of the ink that you're using. Okay, there is a lot of stuff in terms of actually modeling some of these features, in terms of including nonlinearities. So essentially, it's a very, very exciting time given the concurrent advances in manufacturing technology. Okay. So with that, let's look back and ask what do we need to rely on? So essentially, the demands on any of these solvers are very simple. In some sense, they have to span multiple scales. And what I mean is that there'll be regions in the geometry. So let's imagine that I have an aircraft. There'll be regions that are very flat and wonderful. Then all of a sudden, there's a very sharp corner. So the field behavior in different regions of the structure have to be treated differently, right? So you want them to model this different scales of physics. So for instance, if I have an object and I am mounting an antenna on the object, and to give you an example, every time you have I don't know whether you guys know this, but if you were to take out an antenna from a combat aircraft and try and analyze it, that's a huge amount of money that you're taking out and then just replacing it. So fixing it in an experiment or fixing it in reality is an enormous expense. And for you to do it on a desktop, it's almost trivial in terms of cost. So it's much better to design on a computer and figure things out before you can actually design it, before you actually replace an antenna on an aircraft. right? So another thing that you have to do is you have to be better able to represent the underlying physics. So what this means, in some sense, is that you have to somehow there is concurrent advances in both the underlying mathematics and in computer science, as applied to very interesting problems that we as electrical engineers want to be able to solve. So let's get down to this. I'm going to skip this slide for a second. So this is what we've done overall, right? I mean, overall, over the n number of years, we've pretty much done every single thing that you can think of in terms of computational electromagnetics. So that's differential equations, integral equations. We are doing essentially fully coupled circuit and electromagnetic systems. We're doing n-body problems, parallel n-body problems. And a more recent venture has been, how do you develop electromagnetic tools on Pixar surfaces? And I'll talk about that quite a bit in a minute. But I want you to keep that in mind. How do you develop, so that's going to be the main theme of the talk. How do you develop electromagnetic tools on Pixar surfaces? And what do I mean by that? All of you guys, if you've ever watched TV, you've ever played computer games, and you guys are sufficiently old now that I can rely on you to go back in time, you can imagine that n number of years ago, the computer graphics or animation that you saw was extremely coarse. And you would have observed that as time went on, the animation has become better, things are more realistic, things are more detailed, things are phenomenally great. So in some sense, what I'd like to be able to do is ask this question: how can I realize physics? How can I use these wonderful advances in computer graphics? How can I take advantage of that to develop physics on those surfaces as well? Or in other words, what mathematics needs to be done to enable that to happen? And if you're able to do it, there are wonderful advantages that you can bring down the road. Okay, so that's one area that I'm going to talk about. And another thing that I'm going to talk about is n-body problems. So once you develop some of these physics, now you've got to solve it faster. How do you solve it faster? What kind of algorithms do you need to develop to solve it faster? That is really what I'm going to talk about. Okay, so let's go back and revisit our problem. I'm going to set the stage here. So let's imagine that I have some object. I'm essentially illustrating it in 2 dimensions. It's not 2 dimensions, as we'll see in a minute. This is what you're given. So you are asked, you're essentially told that there is some source that you do not know on the surface that exists, that is represented by these dots that you see. I have a Green's function that essentially maps this particular source to a field. And then what you're told is that there is some operator operating on this guy, that is what you see here, that is equal to a given right-hand side. This can be an incident field, this can be a feed to your to an antenna system. And that, what you're really asking is, if I were to be given this, then how can I find this quantity, right? I'm going to try and solve for that particular quantity. Okay. Now, this in some sense is a very, very expensive proposition. But this is the overall picture that I want you to have in mind in terms of a very generic problem description. So how do we typically solve this? The solution procedure, as you can imagine, is I have some kind of an object. I'm going to talk about integral equations, period, in this talk. And if you don't know what I'll try and see if I can describe them along the way. What an integral equation is actually something very simple. If you've done any form of equivalence theorem, essentially we are saying that I have a current that I do not know on a surface. It is defined on a surface. And you know that there is a field that's impinging that is causing that current. Your goal is to say, given the field that's impinging, what is the current that it produces? So it essentially, and that is driven by a convolution with the Green's function. Okay, and I'm sure you must have taken classes with Breton, and he has explained this quite extensively. So with that, let's get into it a little bit. Essentially, what you're doing is that you have a geometry. You're trying to represent the geometry. The geometry, as you can imagine, is not given to you analytically. I mean, I can't give you a geometry of an aircraft analytically. So what you do instead is that you give it a mesh. What is a mesh? A mesh is a collection of piecewise flat triangles that essentially give you a representation of the geometry. Okay. Once you have these piecewise flat collection of triangles or collection of nodes, as you want to think about it, now you say, okay, this is the approximation of the geometry. And on that approximation of the geometry, I'm going to define a function that represents my unknown on that flat representation of the geometry. So you essentially moved away from the true geometry. You've gone to a discrete representation of the geometry. You're on the discrete geometry, and you represent a discrete function on the geometry. Once you do that, then you do all the calculus, whether you're taking a derivative, whether you're convolving, you're doing an integral, you do everything else on that discrete representation with that function that you've defined on this particular geometry. And then you pair it with some acceleration procedure to make it go faster, and you solve, and then you develop a way to validate it, and you go back and you refine it such that you get a measure of confidence in whatever solution you come up with. So this is what exists. Okay, so let's look at, and so this is what I meant by a mesh, right? I mean, so you have a sphere here, you have a collection of facets, or you have a collection of triangles. So if you look at this in low order, you can, and I want you to visualize this, at any given intersection, so I don't know if you guys can see a zoom here, at any given line here, you can imagine two triangles that intersect with each other. And as you can imagine, while they are continuous, in other words, they share the same edge, for instance, their normals are discontinuous, because the normal in one triangle points in one way, the normal in the other triangle points in another way. So these surfaces are, in effect, C0 surfaces, right? And this is true whether you have a higher order representation or a lower order representation, right? So with that, one of the first things that we tried to do was we said, okay, get away from this. And so what we can say is, I have a collection of nodes, and what I'm going to do is I'm going to create a collection of patches, so to speak. Okay, so I'm going to say it is not just restricted to a triangle, but it's, say, a collection of triangles. I'm going to define a smooth parametrization of that particular object. So what we can start out with is a collection of nodes that have oriented normals, and we can define what I call a projection plane. And you'll see this here. I have defined for these oriented nodes, I have defined a common projection plane. And on this projection plane, I can define a representation of this particular surface in terms of its height with reference to its projected coordinate axis in that plane. So I can define a higher order geometry. And what happens is that if I use that higher order geometry, this is the illustration. So in other words, I have defined an R as a function. R is any point on this particular surface in terms of U1 and U2. Once I do that, what I can do is that now I have a higher order. I can do this using a least squares fit. I can do all of this beautiful stuff. And I have something that is smooth across patches. So now I've introduced a notion of overlapping patches, each of which has a description of functions on it, and it is higher order continuous. It is actually wonderful. So you can imagine that if you were to go to something that is an aircraft, and on a wing of an aircraft, you can define that entire wing as one patch. And so you could do very, very interesting things. You could define basis sets that are adapted for a particular location on a geometry. So on a wing, for instance, I can define a function that is a collection of plane waves, so very large domains of support. Near a corner, I can define functions that essentially respect the quasi-singularity around that particular corner. So I can define basis functions that are adaptable. So we have shown that it is adaptable in space, it's adaptable in order, it's adaptable in geometry, all of the kind of beautiful stuff that you would really want in stuff. But the question is that the end of the story? And in some sense it is, but there is something slightly off. What is off is that these surfaces essentially overlap with each other. Because they are defined differently, they are not watertight. In other words, they are as close as you want them to be, but they are not exactly on top of each other. Okay, so because they are not exactly on top of each other, there are small problems that you'd get to. You can kind of mitigate a lot of those things, but the question that we asked ourselves was, are there better ways? Okay, just to give you, let's see if this works. I don't know if this will work. It doesn't work. I'll show you guys at the very end. Apparently, if I use Adobe, all of these hyperlink mappings work, but it doesn't on my presentation screen. So, but we've shown a number of these things, and I'll show you towards the end of the talk some of these more interesting results, right? That said, we can do this for integral equations. We can do this for differential equations as well. Now, so this is what I want you to think about, and this is what I alluded to earlier in the talk. If you look at these flat surfaces that we've been using, or at the GMM surfaces, which is overlapping, you can look at that, and all of these flat surfaces have a common point of origin in terms of computer graphics and in terms of computational physics that we are doing. They were developed in the 1940s, right, or perhaps 1960s kind of a deal. But if you look at it, they have evolved phenomenally. Right? We have used standard Lagrangian surfaces in computational electromagnetics, so computational fluid dynamics and all that. The question that we'd ask ourselves is, why would you want to drive a Chevette as opposed to a Corvette? And I don't know if you know the difference. A Chevette is a clunky old car. For those of you who remember the Ambassador cars, it was actually a stage older than that, which essentially kind of bailed on you every time you turned the key. There have been enormous advances. For instance, NURBS is beautiful, right? Subdivision is a surface description that is very, very simple to realize, but essentially gives you surfaces that are C2 continuous pretty much throughout, other than at isolated points, wherein it is C1 continuous. And there are manifold T-splines and all of that kind of stuff that exists. So there is a whole panoply of wonderful computer graphics tools that all of you guys are familiar with, in the sense that you've used them, you've seen renderings of them that provide. If you've seen Toy Story, for instance, if you can imagine how wonderful that surface was, that is the kind of stuff that we would like to be able to use and do physics on that particular surface. Let's delve into subdivision. What is that? It's actually a very, very simple idea, right? So essentially, you start out with a very, very coarse mesh, and then you refine it once, right? So in some way, I'm going from, let's imagine that I have this facet. I'm going from that facet to I'm moving the nodes. I'm introducing new nodes, and I've moved the locations of these nodes. And this refinement process proceeds infinitely. And on infinitely, you get a surface that is like this. So you can imagine you start out with something very, very coarse, and you get something that is very, very smooth. And of course, I'm sure you're wondering, what is the cost of doing that? Is that expensive? Why would I want to go through infinite refinement? You don't need to. There is a map, an analytical map, that effectively takes you from this geometry all the way to this geometry, directly, without any effort on your part. You store this guy, and you do a little bit of multiplication with polynomials. That essentially takes it from this mesh directly onto this description. And if you look at this description, it's phenomenally smooth. It essentially is C2 continuous. There is no intermediate. I want to emphasize, there is no intermediate refinement. This mesh points to this guy. This mesh points to this guy. This mesh points to this guy. So you might as well start with this guy and effectively work on this guy. Okay, so that is the beauty of a subdivision surface. And these are some other renderings. And if you've watched Cars, for instance, you can almost immediately recognize this. You're not only able to start from something very coarse, you can refine locally. You can refine locally. You can add dimples. You can add whatever you want. And so it is possible for you within this particular framework for you to do all of the wonderful analysis that you are probably familiar with, but it's signal processing. You can do what we call multi-resolution editing, right? You can edit geometries. You can add a few more features that you want. It would be wonderful for you to realize, given these addition of few features, what is the electromagnetic effect down the road. So that is really what our vision in terms of pursuing this research is. Okay. So this is really what the rationale for doing this is, right? So if you look at basic computational electromagnetics, we've gone through leaps and bounds. We've used very, very simple surface constructions. If we were to be able, so the way we've done it is that the underlying surface representation essentially, like I talked about earlier, dictates the underlying physics representation. I'm talking about representations, not the physics of the service. Those are two different things. The underlying representations are tied to each other. So what we're essentially trying to do is somehow divorce the two things. We say, here is a surface representation. Can we use that to create a new underlying physics representation or anything else that you want to do on top of that? Such that it doesn't, because the surface is continuous, you're not constrained as much as you were when you had piecewise flat triangles. Okay. So this is really what we've done. So essentially what we do is we start out, first thing that we have to do, again within the GMM framework, is that we have to define patches. We have to define maps between patches, again, subdivisions. We've got to figure out how to merge. We've got to define partition unity and define basis functions, right? So in the subdivision mesh, if I take this particular guy, this is one subdivision mesh. This subdivision mesh overlaps exactly with this subdivision mesh. So in other words, there is a mapping of elements on this surface directly onto the surface and vice versa. So there is a mapping that goes back and forth. So the way I want you to think of a GMM patch is this guy is patch 1, and this guy shown in a slighter darker shade of red is another patch. They overlap, but this region of overlap essentially offers a map that is a two-way map. So there's a map forward and a map back, right? So you can define all of the maps. So you have continuity of functions throughout, and you can do all kinds of cool things. So you can create. So you have an analytic description of surface. You have an analytic description of all the tangent vectors that you need, and you can construct your basis functions because we're defining vector quantities on the manifold. You can construct it using a composition of tangent vectors. Okay, so essentially this is the definition of basis functions on this particular manifold. Okay, again, for some reason it doesn't work, but trust me, I'll go through a whole bunch of these very colorful figures down the way here. Okay, so that is how you do GMM. Now there is another very, very interesting approach that one can take, right? That interesting approach is what I call an isogeometric method. So let's go back again and look at what we did. We defined a geometry, we defined patches, and then we defined physics on those patches. So what does that mean? Or basis functions to represent physics on those patches. What does that mean? It means that if I were to change the patch description, my basis functions need to change for that particular patch description. So if I use a different polynomial to represent the geometry, then I have to use something slightly different to represent the physics. But suppose I were to be able to do something interesting. And what do I mean by interesting? So suppose I were to be able to say, here is the basis function that I'm going to use to represent the geometry. Okay? And that's it. This is the basis function I'm going to use to represent the geometry. So if I want you to think about a patch in 3 dimensions or a triangle in 3 dimensions, you can represent a plane in 3 dimensions very, very nicely. You can represent a collection of planes in 3 dimensions very, very nicely. And that, by definition, is a geometric basis set. Alternatively, I can say my geometry on this particular surface is say, a spline or a higher order polynomial that essentially has control points on these surfaces. So that's another way of representing geometry. So to think about it, to give it a little more abstraction. So imagine that I'm trying to represent a sphere analytically. How do you represent a sphere analytically? Well, that really is a constant, right? I mean, so essentially, if you represent a sphere, you'd use a very simple representation in terms of analysis. So with that, what I can do is the following. If I can say the basis functions that I use to represent my geometry is the same as the basis functions that I use to represent physics of the geometry, I can realize wonderful things. And this is one thing that I can do. Suppose you're a designer and you were to ask, what happens if my antenna were not pointed has a different endpoint in terms of, imagine that you're doing a logarithmic spiral and you were to say, okay, that curvature is slightly different. if my basis functions for that represented that curvature in terms of, were slightly off and they respect to the same thing, you could change it almost immediately without going into a mesh. From a designer perspective, suppose you were to say, from an inverse problem perspective, if you were to say, hey, if I have, and this is something that is very true, if I have, say, if I have a red blood cell, you can imagine there's a red blood cell that is very nice and flat, and it looks like a torus. It's squished in the middle with a membrane, and if it is healthy, that's how it looks. If it is not healthy, then it's a little bit bloated, right? All of that can be related to geometry. I have a geometry, and all you need to do to optimize this or to try to figure that out is find those coefficients, right? A coefficient that is higher order or that represents the geometry is easier to figure out. The number of unknowns are far less when you have when you have this marriage between geometry and physics of the geometry. So you can do topology optimization, you can do deformations, you can do all kinds of things very, very easily. Okay. So now we can pose the problem slightly differently, right? So what you can do is that you can say, hey, I have a subdivision surface. I'm going to treat that subdivision surface in its limit. I showed you that it reaches a point, and essentially you know exactly what the value at that point is. So, hey, I have a value, and I don't know what that value is, but I'm going to construct a basis set that essentially satisfies a Helmholtz decomposition. And what's a Helmholtz decomposition? You're essentially representing gradient fields, and you're representing rotated fields, right? These are written for a multiply connected object as well. So you'll have both the rotated fields and you'll have a harmonic component that goes all the way around. Okay, so this harmonic component is 0 if the surface is simply connected. So in other words, it does not have holes. So if it's topologically a sphere, then it is perfectly fine. But if it is a donut, or if it is a ring, then it has harmonic components. Okay. It has beautiful properties, as you can imagine. Helmholtz decomposition has beautiful properties, and simply arising because I can represent a gradient field, and I can represent things in terms of a rotation, right? Okay. Now, if I can do that, then I'll show you again in a minute. My apologies. We'll go there as soon as I finish with this. And I don't know how much time I have. I can keep talking, but I want to show you some of these results. You have wonderfully well-conditioned systems. So I can show you systems that are phenomenally well-conditioned in the sense that, so I don't know whether you guys are aware of what condition number, essentially the ramifications of condition number are, but essentially it means that if your condition number is 1, then you're essentially down to identity. So systems are very easily invertible. On the other hand, if your condition number is 10 to the 17, in which cases sometimes they are, then essentially your matrix is singular, and you can't really invert that matrix, because at the end of the day, all systems of equations are written as solutions to a problem in matrix form as AX is equal to B, and your job is to invert A. We can show you, and I'll show you in a minute, results that are not just well-conditioned, but we have accuracies that are just mind-blowing. There are places on again, this is against analytical data on a sphere, wherein you get approximately 5 to 10 digits with almost no effort, okay, as well as yeah, I'll show that in a minute. Okay, I'm going to skip these generalized Debye sources because I think that takes us on a bit of a detour. And let me talk about potential evaluations. So do I have about 20 minutes? Is that about right?
Yes, Professor, you could go ahead.
Okay, fantastic. So what I've talked about so far is, and I haven't shown you any results, and as I said, I promised to show you quite a few results, is that one of the biggest challenges in computing all of these things in terms of an integral equation perspective is the cost. So imagine that you're on a telephone network, and this is an illustration of a telephone network. So I have a whole bunch of observers, and every observer wants to talk to everybody else, or observers, sources, and receivers, right? So everybody wants to talk to everybody else. So as you can imagine, the number of connections that you would have is essentially n squared. And you don't see that, right? I mean, in practice, you don't see a wire between you and everybody else in the world. What you see are essentially hubs or intermediate points, right? So this is incredibly expensive, as you can imagine. from a number of perspectives. So it is very expensive in the sense that any matrix vector product costs n squared, where n is the number of unknowns, and it takes n squared matrix entries to store it as well. So it's very expensive from a memory usage perspective, as well as from a computational cost perspective. And I'll show you results going in a few minutes of things that we are solving that are about 300, 400 million degrees of freedom, right? I mean, so they're very, very large problems. So as you can imagine, if you're trying to do a matrix iteration for something that is 700 million, say, or 300 million, now that is if you're trying to store a matrix that was of that size, you just can't store it, right? So think about it, it's an n squared storage. So if you have 10 to the 9, that is 10 to the 18 complex numbers, well, you can't store that. Right, you need gigantic storage to store it, as well as to both write, store, write, and retrieve as you go through. If you're going to try and invert it, that cost scales as n cubed, which is 10 to the 27, right? I mean, so you just can't do that. It's just incredibly expensive. So what we've been working on for quite a while, and not just us, but a whole bunch of us, has been, how do I reduce this cost in terms of computing this matrix cost from something that scales as n squared to something that scales as ns or n log n, right? So and of course, this is it is not just restricted to points and to problems in electromagnetics. It has very, very wide applications. Essentially, these applications are mind-blowingly wide. So I wanted to think about this statement, right? There are 5 differential equations with constant coefficients that essentially describe 90% of the physics of linear physics, right? They're the Poisson equation, the Helmholtz equation, the wave equation, the fusion equation, and Schrodinger's equation. That's it, right? I mean, so that governs pretty much all of physics, or well, I shouldn't say all, but a whole bunch of things that pretty much are of interest to us. Okay, so I'd like to somehow accelerate it. So, and you guys have come across this in terms of acceleration. So when you do a Fourier transform, you're effectively doing exactly the same thing. Standard Fourier transform is essentially an n squared process. Fast Fourier transform is an n log n process, right? The manipulations that take you from a Fourier transform to a fast Fourier transform essentially are all algebraic. And by the way, this was discovered multiple times. And if you go back, it was one of the top 10 algorithms of the last century, but it has been discovered multiple times throughout history. I think the first person to do it was Gauss. So it goes back that far. Okay, so here it's slightly different. We're not doing algebraic manipulations, but we're doing operator manipulations. Okay, so to give you an example, if you want to think about it from a physics point of view, and these are very interesting physics problems, the Laplace potential is smooth, it decays very, very nicely. Helmholtz potential, a real pain, because essentially you're interested in both the phase as well as magnitude, and that is very, very important, right? But in effect, you can use some of these redundancies to come up with fast methods. Okay, and in some sense, these are all some of the things that we worked on over time, right? I mean, so you have Coulomb, Lennard-Jones, and some of these things are used in molecular dynamics. Some of these are used in nuclear physics, and some of these are used in electromagnetics. And these are problems that we worked on in our group for quite a while. Okay, and this is just a list of things that different people have done. I won't go too much into it. So suppose I'm interested in solving. This is my bias as an electrical engineer, that I'd like to solve very, very large systems. Very specifically, I'd like to be able to go from feature sizes that are sub-wavelength. So when I say sub-wavelength, they are the sizes of these objects. Imagine that I have an antenna, I have a feed on an antenna. That size of that feed is approximately lambda by 1,000. Right? And imagine that antenna were embedded in an object that is 1,000 wavelengths long. So the scales that I'd like to traverse are to essentially capture feature sizes that are lambda divided by 1,000 on objects that are 1,000 lambda long. And that is very, very important for me if I were to be able to capture all of these things self-consistently. Right? So in some sense, what I'd like to be able to do is create this framework, wherein we have very, very small features at this level, medium-sized features at this level, reasonably larger features at this level, and gigantic features at that level, right? I mean, this would be my 1,000 lambda, this would be my lambda by 1,000. So this is the scale that I want to traverse. Okay, so this is really what we're going to talk about. What we have developed in our group over the years is what we call wideband FMM. So it enables you to scale some of these features. I'm not going to give you details of exactly how we do it. So for just in terms of the general audience, if you were to just look at my Google Scholar page, you'll see a lot of different problems. You'll see a lot of different papers that essentially address all of these problems that I'm talking about from a while ago. So one of the main things is whenever you do, like I said, when you do a fast method for a Fourier transform, to go from a Fourier transform for a fast Fourier transform, you're doing algebraic operations. As you can imagine, algebraic operations are identical to machine precision, and that's what you'd find. When you do operator transforms, that is not necessarily the case. But it's also important to make sure that whatever operator transforms you do, you still are able to control error. And that is exactly what I'm showing you. So essentially what I'm showing you is a whole bunch of different dipoles that radiate and receive. They're uniformly distributed in an 8 lambda cube, and I'm essentially computing interactions between them. And all I'm asking is, can I show you that the error decreases as you increase? This chi is an oversampling parameter, and that is indeed the case. So all of them decrease very, very, very nicely. Okay, this is for a uniform distribution. This is for a non-uniform distribution, and as you can see here, errors come out very, very nicely. Okay, now not only did I do FMM, what I did was I added something called ACE, and that essentially is a trigger that enables me to work with feature sizes that are significantly smaller. And that is what this guy is, in which case here I have a uniform tree. In other words, I have trees that are uniformly populated. And I don't know if I so if you think of a decomposition, assume that I have a box, I have divided it up, and every single box has something in it. So this is the non-uniform tree distribution. The main takeaway from both of these guys is that I can control errors very nicely all the way up to about 10 to the minus 6 for a non-uniform tree and 10 to the minus 10. Again, these are essentially what I'm doing is I'm taking a dipole that is arbitrarily oriented in space. There's another received dipole that's arbitrarily oriented in space. I know exactly how to compute the fields sent by this source dipole as measured by this received dipole analytically, and I'm computing it through my approximation method, and I can control errors to 10 to the minus 10. So this is important to me. Using this, I can do a whole bunch of interesting problems. So one of the first things that you do is you'd say, okay, can I solve for scattering from a sphere? How well does it compare with a V series? And I want to point out certain things to you. This is a zoomed in version. The actual signature looks like this. This is also a zoomed in version. I'm zooming into a very, very small portion of it. This guy is 256 lambda. This is 512 lambda. This is represented discretely using triangular patches, using 85 million degrees of freedom. This is 340 million degrees of freedom. So I just want you to think of the scale of these problems, right? I mean, so 512 wavelengths is a huge problem. This is a sphere, and you're probably asking me, why the hell do I care whether it is, if it's a sphere, it doesn't really matter. What I'm really trying to do is compare our numerical discretization with something that is analytic, because in the next problem, I don't have an analytic solution, right? I need to build confidence. This is a very large problem. This is 128 wavelengths long. This is an arrowhead, So think of somebody with an arrow, it's a tip of an arrow. And so it is a challenging problem simply because it has very sharp features there, sharp tips, all of that kind of features essentially make it a very challenging problem to solve. This is 128 wavelengths in length, so that is the length is 128 wavelengths. It doesn't occupy a volume, so it has only about 19 million degrees of freedom. Okay, this is how well it performs, but it's different RCS cross sections at different cuts. Now, I don't know what happened here, guys. Oh, there it is. Now it's better. So this is a much larger problem. This is this is a Boeing aircraft. This is 755 wavelengths long. And as you can imagine, if something is 755 wavelengths long, you're really approaching realistic sizes at some of these frequencies, right? We are discretizing it using about 285 million degrees of freedom. So you have very large amount of discretization, and you can actually solve these problems in real time. It doesn't take months and years to solve it. It takes a few hours, right? So with that, what I'm going to do is I'll come back to the summary. I want to show you some results before I come back to the summary. Okay. So this is results on GMM that I talked about. This is measured data. This is GMM on a cube, backscatter data. I'm essentially I have GMM, I have RWG, and I have measured over a range of frequencies. Right. Likewise, I have a sphere and a cone sphere, and I'm showing you convergence. This is a slightly different problem. I have different. I don't know if you guys can see this. Again, GMM. I'm using different basis functions here as I'm using here. So it's very easy to stitch different basis functions in different regions together. Likewise, I have, let's say I have a box. I have different basis functions in this domain as I have basis functions of this domain. So in one, I'm using plane waves, and the other one, in this region, I'm using plane waves to represent it. In this region, I'm using RWG because RWG is better for edges. So I'm using different mixtures of quantities just to optimize the number of things that I can do. Right? These meshes are non-conformal as well, and as you can see, you can deal with a whole bunch of different stuff. So let me show you. This is something that you guys might recognize. This is a bent waveguide. I'm again using it in say this region. I use a different set of basis functions compared to that particular region, right? And it is pretty much on top of stuff that you know, but with far fewer number of degrees of freedom. Okay, this is another S-band wave. There's another weird waveguide. I'm using again different orders of basis functions. If you can see it, I have linear basis functions or quadratic in some of these regions, and they're pretty much right on top with whatever you can get from something analytical. That said, let me show you something slightly different. This is what I would like you to take away with. These are toruses, bent toruses. What I'm using is a subdivision surface that I talked to you about earlier, right? So you can do very, very complicated stuff. So for instance, this is the Shmutov surface. The reason I'm interested in these surfaces, and that's a question that I can ask, is that some of these surfaces are emblematic of what is found naturally in wings of butterflies, for instance. You find surfaces that are represented using this. So if you were to think about it, a butterfly wings, for instance, or the iridescent feathers of a bird are largely photonic effects, and they're not iridescent effects. In other words, they are colorful because of the periodic structure in their wings, in the makeup of their wings, right? And this is essentially what you're modeling. Okay, let me show you what this IGA stuff is, and then I'll come back. So this is the IGA results that I told you about. This is how good our condition numbers are. If you play with it a little bit, your condition numbers are essentially down here or here, which is just ridiculous, right? If a condition number is, like I told you, as you come closer and closer to 1, if the condition number is 1, it is readily invertible. So these condition numbers are just mind-blowingly good, as you can see from all these figures, right? Our errors, and this is I think my errors are on the next page, but I'll show them to you in a minute, okay, here are my errors, right? This is the isogeometric analysis that I promised a while ago, wherein I'm using the same basis functions to represent the geometry as I'm using to represent the currents of the geometry. And this is a pointwise error of the currents, both real and imaginary. And my errors in the currents, not in the radiated field, and I want to emphasize that, it peaks at 10 to the negative 5, which is phenomenal for currents. Okay, and you can do very complex, reasonably complex objects. If you go onto archive and you go onto some of these other things, you'll see much more recent results that are out in the public domain on a lot of these methods, and where we have come with this in terms of shape optimization, in terms of inverse scattering, in terms of a whole bunch of different things. So with that, let me return to my summary. This is something, just to give you an idea, this is some things that we've been doing over the past 8 to 10 years or so. We have not taken, in our group, we don't do the usual stuff, in the sense that we try and figure out whether there's some interesting marriage between physics and mathematics and geometry, largely because we're interested in a whole bunch of emerging problems. And some of these emerging problems are topology optimization, they are designer optics, they are quantum computing, and a lot of these things can be used for optimizing topology and photonic structures, right? But wanting to do that essentially means that you have to develop the necessary infrastructure. What I mean by infrastructure is the mathematical infrastructure, the algorithmic infrastructure, and from mathematical infrastructure, I mean, what are the kinds of solvers that you'd like to use? How would you like to mesh it? Is it possible to obtain solutions to these problems in real time? And that is essentially what we do. And this is, again, just a snapshot. There are members in our group who actually work on what we call particle and cell cores, which are very different, and I've not talked about that here at all. That is extremely useful when you're trying to understand interactions of plasma with an underlying electromagnetic field. We're looking at quantum dots and how you can use quantum dots within photonic cavities, fully coupled quantum dots, not the homogenized version wherein you just deal with the background media, or micromagnetics, and you'll see some work on topology optimization if you were to look at it. There's just a snapshot. It'll be good to hear from you guys. And just a bit of a pitch. We have one of the strongest electromagnetic groups at least in the US, about 9 to 10 faculty members who collaborate very, very regularly. Our group size is about between of the hardcore AP-MTT crowd. I think we have a group that is around 35 to 40 students amongst 3 faculty members. And if you were to include the other group within ECE and physics, who are interested in a whole range of problems that leverage off some of these things, our group size would easily top about 60 students with about 9 to 10 faculty members. So with that, I'd love to take questions. Sorry for going just a little bit too long.
Questions from the audience, please.
I guess it was phenomenally clear.
Yeah, you are clear. I guess like, had it been a little bit larger, then it would have been more clear. So, but anyway, it's okay. Any questions from the audience?
Yes, Professor Shanker? Yeah.
Yes.
Sir, could you little bit explain more around, like, I really like your butterfly kind of thing, like that you said about this periodicity and something like that. So could you be more elaborate on this particular point?
Sure. I saw a question pop up in chat. Let me address that, and then I'll address your point.
Yeah, sure.
So let's think of a higher order geometry and a low order geometry. Let's just understand that. So imagine that I have a collection of triangles on a flat surface, right? So if I have a collection of triangles and I take let's take 2 triangles, and and they essentially meet on an edge. I hope you guys can see that. And as I bend the edge, what do you see? You see that the 2 surfaces intersect at a common edge. So in other words, they are C0 continuous. They're continuous, but the normals are not. What is the normal related to? The normal is related to the derivative. So the derivative of a patch, the derivative of this particular surface, or the gradient of this particular surface is a vector that points this way, and the gradient of this particular surface is a vector that points in this direction, right? So these are the two directions. So in other words, the function is continuous, but it's not derivative continuous. Now, suppose you were to not do that, and let's roll back and think of interpolation on a line. So if I were to think of a line, how can you interpolate any function? One way to interpolate any function, what do I mean by interpolation? I have a set of values at a given set of points, and I'm trying to figure out what is the value in between. So one way you can find the value in between is you can say, okay, I have this and this value, and I'm going to take an average, right? Or a weighted average. A weighted average would be equivalent to a linear interpolation. Alternatively, you can define what are called B-splines along a line. On B-splines, you can say, I would require to have an n-fold continuity along the line, right? So you can come up with functions that are continuous, that are continuous even for interpolating functions on a line. And that's really what I mean by continuous functions on a manifold. The question is, how do I represent a manifold using a collection of functions that have higher order continuity built in? Does that make sense? This is something that is very that you guys use all the time when you do computer graphics. In some sense, you can actually go to Pixar's website and you can download these codes. Right? You can just download a code, and that'll give you a higher order continuous surface. Okay. So I hope I answered your question. If not, just shoot a text here and I can see it. So to answer the next question, so if you look at structures, and I think this was in a JOSA paper that I published a while ago. If you look at structures in say the butterfly wings, and if you look at the topology of the structure in butterfly wings, what you see is that the structure, the color that comes about in there is due to periodicity of the structure of the wing itself. Right? If you look at if you take the wing and put it under an SEM machine, you'll see that it has very well-defined periodic elements along the axial directions. And that is responsible for the color. It is that periodicity that is responsible for the color. Does that make sense?
Yes, sir.
And that is true for not just butterflies, it's true for a lot of birds. So it is not, so when I say iridescent, I'm essentially saying there are no dyes that produce that color. That color that you see is because of structure. There are wonderful books that you can pick out on structure and color of butterfly wings. And that is something that is very heavily investigated, actually. So I don't know if you, I don't know if you guys are familiar with cuttlefish. If you're not, it is not a bad idea for you to watch a YouTube video that takes about 10 minutes or so on the magic of cuttlefish. So if you look at cuttlefish, it essentially morphs its skin so that it blends into its background. You can't see it. It makes itself invisible. And the way it does it is it does it by stretching its cellular structure. Right? So it has photoreceptors, it stretches its cellular structure so as to match periodicity and therefore becomes invisible. So all of this is structural. It is not anything else. So the idea of biologically inspired photonic structures is wide open. It's actually beautiful.
Thank you, Professor. It was really nice to get this insights about periodicity and structures.
So there was another question. So in order to, so some of the stuff, the best way to learn some of this stuff. So I don't know what the starting point is. The starting point is actually very classical. So I would recommend standard books in computational electromagnetics. Don't go to the advanced books. Learn some of the standard books. And I think there are books by Jiaming Jin, for instance, that covers a lot of lot of the fundamental background, not necessarily these areas. But once you come closer and closer, I think the only recourse, unfortunately, is journal papers. I'm too lazy to write a book. Oh, okay. So the question. Okay. So the question was, how if you're unaware of the current structure, how do you choose a basis function? Okay. So let's look at what we do, right? So we know certain properties that the basis function has to satisfy for the current. The currents have to satisfy. The currents. If you were to solve the electric field equation, or if you were to solve for a dielectric object, and you're solving for the equivalent current, you need it to be what we call divergence conforming. What does that mean? You need not only to represent the current, but also the charge that goes with it, right? So because if you look at your electric field, you have the vector potential contribution as well as the scalar potential contribution, right? So if you look at those, you need those two things to be satisfied. So the underlying thing that you need is that you have to choose basis functions that are called div-conforming basis functions. So any basis function that satisfies that is your proper candidate. Now, in the literature, in most of these codes, you just choose them. What do they behave like? They essentially make sure that if I'm on two triangles that meet, that there are no line charges along the intersection of these two triangles. So in other words, the current comes here and goes continuously into this domain. So there is no discontinuity to a line charge. So those are the simplest basis functions that you would choose. Now, as you go to more complex geometries, and more complex geometric descriptions that allow higher order continuity, then these properties are automatically satisfied for those basis functions, like what I told you. Before I forget, if you really want to understand some of these very nice properties, there is a book by Andrew Peterson called Mapped Basis Functions. How do I write it here? Maybe I have to share my screen again. Let me share my screen and I'll show you. I'll write out the name of the book. So please look at this book. Look at this author. So he has written about 2 or 3 books. One basically on computational electromagnetics, another one on basis functions, and a couple of other books. So this is a wonderful read. He is one of the leaders. He's in our field. He's phenomenally well known and has done some wonderful work in the past. This is another book. Jiaming Jin. He's written what is arguably considered to be the classic on finite element methods, right? So I would search for these 2 authors essentially to get a background into most of computational, most of the standard techniques used for computational electromagnetics. Of course, you won't find some of these more advanced topics in there simply because those books do not exist as yet.
Any more questions? I have a question, Professor Balasubramaniam.
Sure.
So these methods have been obviously extended to other kinds of media like anisotropic media or those kinds of media. Like, what has the role of the media? How can it be best modeled through these techniques, which are extremely powerful, I guess?
You've asked one of the most difficult questions imaginable. So there's a short answer to that. So a lot of these methods a lot of the integral equation-based methods cannot work for anisotropic materials, right? So you would rather use a differential equation-based method for anisotropic coatings.
Okay.
So the way in which I envision using some of these tools is that imagine that I have a domain. That domain contains a mixture of piecewise properties. What I mean by that is that I have some region in space that is homogeneous dielectric. There's another region in space it could be inhomogeneous dielectric. There could be another region in space that could be anisotropic. The way I would stitch them together, and this is what we've done in the past, is essentially use the power of both integral and differential equation techniques to work side by side.
Okay.
Wherein you define these regions and you define interface conditions across these regions that the boundary conditions need to satisfy. Right? So in other words, if I have two regions that touch, essentially you need to satisfy the tangential continuity of electric and magnetic fields. Right? And then you can define equivalent currents and derive this composite breakdown of the domain such that you can satisfy it. So that's how I would include anisotropy, that's how I would include inhomogeneity into this particular framework. So, and this happens very often, right? So for instance, if I'm on a ground plane and my ground plane is anisotropic, well, I can use, and I need to model all of free space. Well, I have to use something slightly different.
Okay.
So you've got to piece things together.
So if you don't have any questions, so it was a very interesting talk. We all learned a lot of things from this. We essentially, our group works in the simulation. We also have a good microwave group that works in all aspects of electromagnetics, in antennas and in microwave circuits and in waveguides. We personally work on the Green's function, but more on the spectral domain Green's function techniques. So it was very, very, very instructive for us, and it really, extends our thoughts to different domains which we have not explored as yet. But yeah, that has been very, very informative talk.
Thanks a ton, Bratin. Thanks for reaching out to me. It was wonderful.
Thanks.
I think this is the largest group. This is the largest EM group in India, I think. So.
Yeah, sure. You are more than welcome to come and visit our institute when you are in India. I would be very happy and share with us some time and share your research with us.
Yep, will do. Hopefully we can travel soon.
Sure. Hopefully Corona is going to let us travel.
Yes, exactly.
Sure. Okay, thanks a lot then, Professor Subramaniam. So, on behalf of our institute and on behalf of the microwave group, we would like to extend our sincere thanks to you and for taking all the time and the pain to illuminate us on your research work.
Thank you so much. It was good seeing all of you. So, I will. If you guys have any other questions, just shoot me an email. You guys know my email, so.
Sure.
See you guys.